So today we're going to be talking about complex zeros and using the degrees to determine how many zeros that we have, real and non-real. Up until now we've been basically dealing with real, but now we're going to see both. So if we have a degree of 4, we're actually going to be finding 4 of the solutions. Some may be real and some may be non-real, but together they will add up to be 4. We're going to skip on down to the linear factorization theorem, where it says that you have exactly that many factors to make up that degree. You have a leading coefficient, and then the complex zeros, or the z's here, make up your complex zeros. The z's are not necessarily distinct numbers. Some of them may be repeated. We've seen that before, something that we have not talked, or that we have talked about before. We also know that when we're talking about a polynomial function, that if k is a complex number, then we also know that k is a solution or a root. Sorry about that. K is also a 0, and then k, x minus k, is also a factor. These are all synonymous to meaning the same thing. And that is for non-real numbers. But the one thing that we can't say is that complex zeros are x-intercepts. They are not. They are solutions, they're roots, they're zeros, they're factors, but they are not x-intercepts. Only your real solutions would be x-intercepts. So we're going to go and we're going to look at some examples here on how to actually write the polynomial function in standard form given two roots. So we have x minus 3i times x plus 3i. So I'm going to use what we call the box method here. I'm just going to draw a box, and it's going to be a 2 by 2 box because of a binomial times a binomial. X and negative 3i in one box, x and a positive 3i in the other box. And what fills in is the multiplication of what's on the outside. So x times x is x squared. And then I get a negative 3ix. I always make my boxes way too small. X times 3i is 3ix, or 3xi, it doesn't matter. And then my negative 3i times 3i is a negative 9i squared. Now we remember from previous lessons that I is equivalent to the square root of negative 1, whereas I squared then is equivalent to negative 1. And so if I have a negative 9i squared, that's the same thing as saying negative 9 times negative 1, which is actually a positive 9. So I multiply on the outside, I add on the inside. So I'm left with x squared, my 3ix's cancel, plus 9 is how I end up with my answer. Then it says I want to actually find what the x-intercepts are and the zeros, if there are any x-intercepts, but what the zeros are. And I notice that my factors are both complex, they're non-real, and so by taking the opposite of both of those, setting those both equal to 0, I can see that I have my zeros are going to be x equals plus or minus 3i, is how I would work that. Then, moving on to the next one, I have 3 factors that I need to multiply, and given 3 factors, I'm going to take my 2 complex, my 2 imaginary, and I'm going to multiply those first. Again, I can be using the box method for that. Just makes it a little bit easier. Again, not necessary. Don't have to. Just depends on how you were taught to multiply polynomials. So I get x, negative I root 2, x, I root 2. I get my x squared. I get my negative xi root 2. I get my positive xi root 2, and then again I get my negative I squared, and root 2 times root 2 is 2. So I'm going to clean this up. 2, so I get a negative 2i squared. I know that I squared is negative 1, so I actually end up with a positive 2. So what I have here is x minus 5 times x squared, my negative xi root 2 and my positive xi root 2 cancel out, and I'm left with plus 2. Now I'm going to multiply those two. And again, I can use the box, a 2 by 2. And I'm left with x minus 5 on top, x squared, 2 on the side. So I'm left with x cubed, negative 5x squared, 2x, and negative 10. I'm just multiplying what's on the outside, and then I add what's on the inside. I end up with x cubed, that is a negative 5x squared, 2x minus 10 is my final answer. And then my zeros to put it, and that's putting it into standard form. My zeros end up to be positive 5 and plus or minus I root 2. Just by setting my factors equal to 0 is where those zeros came from. Now down here with complex conjugate zeros, all that is saying is that if I have an imaginary factor of a plus bi, then its conjugate is also a factor. So basically what we're saying here is that imaginary roots must come in pairs. They must come in pairs. And at school, I had talked about how scorpions also come in pairs. And so it's just like a scorpion, it must come in pair. But with a complex root, it is the conjugate. So if it's a plus bi, then a minus bi is also a root. We turn over to the back side, and we've got quite a few examples here, and I'm just going to pick 2 or 3 of them on the back just to save some time. And I have here a polynomial of minimum degree in standard form with real coefficients whose zeros include. So I've got 2, negative 3, and 1 plus I. So what I'm going to do is I'm going to first start by writing the function using the zeros that are given. So I have x minus 2, x plus 3, because I take the opposite of those when I'm putting in for zeros. And then because it's always x minus, it's x minus 1 plus I, and then x minus 1 minus I. Because if 1 plus I is a factor, then 1 minus I is also a factor. Now I'm going to simplify this, and I get x minus 2 times x plus 3 times, and I'm going to distribute that negative to everything inside that parenthesis. I get x minus 1 minus I and x minus 1 plus I. So now I have 2 binomials that are going to be multiplied by those 2 trinomials. And before I do anything, I'm going to multiply my binomials together, and then I'm going to multiply my trinomials together, and I'm going to get a great big long thing, and then I'm going to multiply all of that together. So basically, what we're looking at is a lot of multiplying polynomials as we move forward, okay? And again, to make it clean and neat, I'm going to use, again, the box method, okay? So my x minus 2 and my x plus 3 I'm going to do out here, negative 2 and 3, so I get x squared, negative 2x, 3x, and negative 6, okay? So I end up with x squared, and 3x minus 2x leaves me with 1x minus 6, okay? So there's that trinomial. Now I get to multiply this fun thing. I'm going to do that up here. And this is going to be a 3 by 3. Again, why do I make my boxes so small? I have no idea. So I have x, negative 1, negative I, x1, and positive I. So I get x squared minus 1x and a negative xi. I get 1x, negative 1, negative I. xi, negative I, and negative I squared. Okay, so now I'm going to combine them together. So I get, actually I can do that out here, I get an x squared, and then my negative 1x and positive 1x, that cancels out. Actually, this is a negative 1x here. I forgot to transfer over the negative from that. So that should be a negative 1. So I should have a negative 2x, because negative 1x plus negative 1x is negative 2x. And then my negative xi and positive xi cancel. And there's a negative 1 here. My I, and then this should be a positive I because that's a negative times 1. Those cancel, so I'm left with negative 1 here. I'm going to hold off to that because negative I squared. If I squared is negative 1, and then I'm taking the negative of it, I actually end up to be a positive 1. So this out here actually equals 1. So I end up with x squared minus 2x minus, or positive 1 plus 1 leaves me with a positive 2. So that is my x squared minus 2x plus 2. Because this is a positive 1, this is a positive 1, my negative I squared equals 1. So that 1 plus that 1 gives me that 2. Okay, so now, and I'm going to make my boxes bigger, I promise. Better for you, better for me. Okay, so now I'm left with x squared, 1x, and negative 6, x squared, negative 2x, and 2. So I end up with x to the 4th, x cubed, negative 6x squared, negative 2x cubed, negative 2x squared, and 12x. This is 2x squared, 2x, and negative 12. So my final answer becomes x to the 4th, and then my negative 2x cubed plus x cubed leaves me with negative 1x cubed, 2x, and that negative 2x, those cancel, left with negative 6x squared, 2x plus 12x is 14x, and then my negative 12 is my final answer. I'm not going to do this middle one because it's the same as this, exact same, and so you can work that on your own. I am going to move down here to finding the zeros and writing it in linear factorization. That means I'm going to work backwards from what I did here. So here I was given the zeros, wrote it as factors, and multiplied it out. On this example, the function is written out, and now I'm basically going to be factoring it to write it in factored form. So here, I first have to graph to find my zeros. So I graph it on the calculator, and I find that it crosses the x-axis at negative 2, 1, and 4. So that came from my graph, and I don't have my calculator right handy, otherwise I would show you where that came from, but you'll be able to see by looking at the graph itself that it crosses the x-axis at negative 2, 1, and 4, or you could look at the table and see that this is where y is equal to 0 at those spots. Now I'm going to go into synthetic division using my zeros. So I have 1, negative 3, negative 5, 5, negative 6, and 8. And those are my coefficients that I only use with synthetic division. So now I'm going to use my zeros that I found. Doesn't matter the order. I'll just start with negative 2, that's first. So drop the first term down, multiply on the outside, add on the inside. Multiply on the outside, add on the inside. Multiply, add, multiply, add, multiply, add, and you better end up with a 0 remainder. Now, I need to do this again because I have 3 zeros. Drop down the 1, multiply, add, multiply, add, multiply, add, multiply, add. One more time. Drop down, multiply, add, multiply, add, multiply, add. So now I'm left with my quadratic of x squared plus 1 because this is my x to the 5th, x to the 4th, x cubed, x squared. So I get x squared plus 1 equals 0. It says to use the quadratic formula, but with just 2 terms, I'm going to just use square roots. Subtract 1 from both sides, take the square root, and I get x equals plus or minus the square root of negative 1. I do know that the square root of negative 1 is I, so I get x equals plus or minus I. So it says, going back to the original directions, to write it as linear factorization. That means I need to write it in factored form using my zeros. So I get x plus 2, x minus 1, x minus 4, and x plus I, and x minus I. Ran out of room, so I just putting those, assuming that this is multiplied together here. X plus 2, x minus 1, times x minus 4, times x plus I, times x minus I. There's my plus or minus right there. That is linear factorization. Now, one other way in which we can write this is through irreducible. And so linear and irreducible. With irreducible, this means that if I would reduce it down further, like this quadratic here, I don't want any complex numbers. I don't want any imaginary solutions. I want it all to be real. So I'm going to start and use the exact same steps that I had used above, and this time I'm going to graph to find my zeros, and I found that there's only one zero, and it crosses at 2, one real zero, I should clarify. So I use synthetic, 1, negative 1, 1, negative 6 are my coefficients. 2, bring this down, multiply, add, multiply, add, multiply, add. So I'm left with x squared plus x plus 3. Now, if I would factor that, of which I cannot, I know that it only crossed the x-axis in one place, so therefore I know that these must be imaginary. So to write it as linear and irreducible, the linear part I've got as x minus 2, because I'm bringing in that 0, but instead of finding the imaginary, like plugging that into my calculator using the quadratic formula and finding the imaginary, I leave it as a quadratic. That is what irreducible means, is that if I would reduce this, if I would break it down to other factors, I would end up with imaginary numbers. Irreducible says no imaginary numbers at all. That is linear. Each one of these factors, when it's linear factorization, each one has a degree of 1. I think I failed to mention that above, but each one of these has a degree of 1 when it's linear. Irreducible, if I would break it down into other factors, those factors would result in imaginary, so I need to go back and leave it as unreduced, basically is how you would say that.